Section 10.4 is on infinite geometric series. An infinite geometric series has an infinite number of terms. A convergent series has a sum that converges to or approaches a specific or finite value. And in this case, the absolute value of r has to be less than 1. Take a look at this little image from your textbook. So along the bottom here we have the number of terms, and then on the y-axis we have the sum of the terms. And you can see that for this series, which is 5 plus 2.5 plus 1.25 and so on, the sum of the terms is approaching the value of 10. So that's a convergent series because it approaches the sum of 10. A divergent series does not have a sum that converges to a specific value. In this case, the absolute value of r is greater than or equal to 1. And here's a little image from your textbook that shows a divergent series. So again, we have the number of terms and then on the x-axis and the sum of the terms on the y-axis. And you'll see that it just kind of continues to grow basically exponentially and does not reach or head towards a sum, a finite sum. So let's take a look at a couple examples here. This says determine whether each infinite geometric series is convergent or divergent. So in the first case we have 2 plus 3 plus 4.5 plus so on. First thing we need to do is, the main thing we need to do is figure out what r is. Remember that to find r, since we know that this is geometric, we're going to take the second term and divide it by the first term. So in this case, r is 3 over 2. Which is 1.5 if you prefer decimals. So r is greater than or equal to 1. Therefore, this is divergent and does not approach a sum. Our second example, 100 plus 50 plus 25 plus so on. Again, let's figure out what r is. So to figure out r, I'm going to do my second term divided by my first term. 50 over 100. r is equal to 1/2. Or 0.5 if you prefer. So r is less than 1, oops, not less than or equal to, less than 1. Therefore, this series is convergent. Here's the formula for the sum of an infinite geometric series. S equals a sub 1, which we call as the first term of the series, divided by 1 minus r. And recall again that if the absolute value of r is greater than or equal to 1, the series has no sum. So let's take a look at several examples here. Find the sum of each of these series if it exists. So we have 4 minus 2 plus 1 minus 1/2 plus so on. So let's find r. r is equal to our second term, which is negative 2, divided by 4, which is negative 1/2, or negative 0.5. So this sum does exist. So let's use our formula. S equals a sub 1 over 1 minus r. A sub 1 is my first term, which is 4, divided by 1 minus a negative 1/2, or 4 divided by 1.5, which is equal to 2 2/3. I switched over to a fraction here because that would be a little more exact. Second example here, 16 plus 20 plus 25 plus so on. Let's first find out what our r is. So r is going to be equal to 20 over 16, which is equal to 1.25, which is greater than 1. Well, not greater than or equal to, actually greater than 1. Okay, therefore, this series is divergent and the sum does not exist. Okay. And our last example of this type is going to use our sigma notation that we've seen in previous sections. So here we have 12 times 3/4 raised to the power of k minus 1. My first value of k is going to be 1, and since it's an infinite series, my last value of k is going to be infinity. So looking at this, I realize that r is equal to 3/4. Remember, that's whatever your base raised to the power is. Okay, so this sum does exist since that is less than 1. So using my formula, S equals a sub 1 over 1 minus r. I need to figure out what a sub 1 is. So a sub 1 is what I get when I put my first value of k into this formula here. So 12 times 3/4 raised to the 1 minus 1, or 12 times 3/4 to the 0. 3/4 to the 0 is 1. So my first value, a sub 1, my first value is 12. So plugging that in, I have 12 over 1 minus 3/4, which is equal to, this is equal to 12 over 1/4, or 48. So the sum of this series is 48. A repeating decimal is actually the sum of an infinite geometric series. So for example, if I have 0.63 repeating, that's equal to 0.63 plus 0.0063 plus 0.000063, and so on. Notice the number of zeros in front of the 63 is increasing by 2 every time. So the formula for the sum of an infinite series can be used to convert a repeating decimal into a fraction. So here we have, write 0.21 repeating as a fraction. So 0.21 repeating is equal to 0.21 plus 0.0021 plus 0.123421, whoops, 1, and so on. Okay, so looking at this, my a sub 1 is 0.21, and my ratio is 0.0021 divided by 0.21, or 1/100th. I'm going to go ahead with fractions. You could use decimals also. So using my formula, S equals a sub 1 over 1 minus r. So 0.21 divided by 1 minus, you know what I'm going to do is I'm going to make this into, I kind of like fractions. 0.21 is 21 over 100. That's my a sub 1 over 1 minus 1 over 100, or that's equal to 21 over 100 divided by 99 over 100, which is equal to 21 over 99, and dividing everything by 3, I'll have 7 over 33. So 0.21 repeating can also be written as 7 over 33. Now there actually is another way that you can do this, and this is kind of funky. So if we say x equals 0.21 repeating, okay, that means that x is equal to 0.2121, and so on. Okay, multiply both sides of that by 100. So I'm going to multiply both sides by 100, and I chose 100 because I have two decimal places, which is the hundredths. So that's going to give me 21.21 repeating, and so on. Now let's take this this line right here of x, okay, and let's subtract that x on both sides. So then subtract 0.2121, and so on. So 100 minus 1 is 99. X, 21.21 repeating, minus 0.21 gives me just 21. Dividing both sides by 99, I have 21 over 99. And then dividing top and bottom by 3, I have 7 over 33. So either one of those methods works. So in this section we took a look at infinite geometric series and figured out how to determine whether they are convergent or divergent and how to find their sums.